introduce today. It's my pleasure to introduce today Haiyang Wang from the University of Copenhagen. He graduated and did a master's in geoscience in China at China University of Petroleum in Beijing. Then moved on to do a PhD from Australian National University in 2018, changing to astronomy and exoplanets. After that, he worked in industry for a year in a company as a geoscientist, then was a postdoc at the ETH Zurich, and he just recently moved, taking a position as an assistant professor at the University of Copenhagen. His interests go around the solar system and exoplanet systems. He has developed models around understanding the connection between the chemical compositions of stars and their planets. And today he'll be talking about very interesting work on the chemical abundances in M-dwarfs and how they compare to the more traditionally studied objects for the chemical evolution of the Milky Way using J and K dwarfs. Haiyang, please.
Yeah, thanks a lot. Thanks a lot for the invitation. And it's really great pleasure to give this seminar to our IoT5 folks. As the subtitle here, this is the exoplanetology perspective. So this actually just try to limit that the implication of this work, and also from the point of view that I'm a heavy user of the stellar properties, particularly the composition, to understand the planetary properties. And I will talk about the lessons that we learned through this process over the past few years, and also the difficulties that now we are encountering, particularly try to characterize the planets around M-dwarfs. So hopefully we can actually bridge this gap and then work together to figure out what's going on and what we can do better from the both sides. Okay, so on the motivation side, so the stars, discrete planets are born from the same molecule class and are therefore genetically interconnected. And I suppose most of us would agree here. And a primary genetic connection is their chemical makeups. So indeed, and with the stellar spectroscopy, one of the most important properties that we learn from the stars is their composition for their photospheres. And here I show the list of the elements that we can analyze, but of course it's not limited to this. But these are the elements that are most interesting to the characterization of the rocky planet, as it contains both the rock-forming elements such as the carbon, oxygen, magnesium, silicon, and also metals. Here I mean the real metal like iron and nickel. So with this elemental composition that we learn from stars, and to the first order, actually we can already to qualitatively to understand the implication for the planetary property, such as we use this set of like key elemental ratios, such as magnesium to silicon, carbon to oxygen, and magnesium to iron ratio, by using their different implications for the geochemical properties, such as the carbon to oxygen. If you have the higher ratio, then that can potentially imply that if there's a planet orbiting such stars, it might develop like a carbon-rich scenario, or otherwise it will be like silicon-rich planet, more like our terrestrial planet. So, and the brighter yellow dot showing the solar composition, and red and yellow shows the data points from the different catalogs. And for like a magnesium to iron, so because magnesium is the lithophile element and iron is the hydrophile, so lithophile means that the element will potentially preferably in the mantle, while for hydrophile preferably in the core, like iron. So a higher magnesium to iron ratio that may imply that the planet may develop a smaller core, or otherwise it will be like a larger core. So for the y-axis, like the magnetosilicon ratio, that it can tell you further about what kind of minor rock that you could develop if you know that the planet is silicate dominant. Such as with the higher magnetosilicon ratio, you might develop the ordinary minerals, or otherwise it will be like peroxide minerals. So just to give an example that why this is, why understanding this different mineral phase is important, is that the olivine is less porous than peroxide, so it will potentially have the less capacity to store water in the planet mantle if the planet is dominated by the olivine instead of the peroxide. So this would have like a implication for that we all care about if that occurs, if that water exists in a planet.
I can't understand him.
So I heard something you can hear me, or Andrea? Okay, so yeah, okay. So if in case any question, feel free to stop me. Yes. So instead of I would go for that. Okay, so this just highlights what the property we can learn to the first order from what we measure from the stars to imply for planetary properties. Even it was not clear enough. Okay, so now that even though we have these connections between stars and planets, so but the connection is not one-to-one, particularly for the rocky planets. That's potentially influenced by so-called devolatilization process, which is the depletion of volatiles in rocky planet relative to the host star. So this has been understood with the solar system data over the past decades, and particularly give this schematic diagram, which shows that for refractory element, which are also called the rock-forming element. So this shows its identity between the rocky planet and the protosun if you do the proper normalization. While for the element with like a lower or with higher volatility, like carbon, oxygen, sulfur, phosphorus, and they will show this systematic depletion in rocky planet relative to the star. So actually, this is what we call nowadays as the devolatilization pattern, as we observe from our solar system data, as I show here first with the Sun to Earth scenario, with the yellow pattern shows the protosolar compensation, and the dots show the bulk Earth compensation, and by normalized bulk Earth compensation to the protosolar compensation to aluminum, because aluminum is one of the most refractory elements. So in that sense, actually, that we could bring a lot of these refractories, also called rock-forming elements, and to the unity line between the Sun and the Earth. Where for this moderated volatile, this shows it systematic depletion, and the difference between the two, which is can be quantified to lead to the first order trend of devolatilization. And this also can actually expand to other solar system rock bodies if we show them as well on this plot I show with Venus, Mars, as well as a few like meteoritic data. You see the variation of this devolatilization in these rocky bodies relative to the Sun. But the scale of the devolatilization vary, but the phenomena is universal, present across these rocky bodies. So this is not only observed for the solar system, it's also observed now for the exoplanet system, particularly from the lessons that we learned from the polluted weather dwarfs. So in terms of polluted weather dwarfs, here is that because these supposed to be that for weather dwarfs, they should not have like a bunting like a rock-forming element because their evolution process. However, for some like a weather dwarf, now we can observe they show is abundant like a magnesium silicon iron present in the photosphere of them, and this was interpreted to be the material that polluting the weather dwarf that was once the planetary precursors. And with this polluted weather data compared to the solar system rocky bodies data on the left side, and you might see the remarkable similarity between the two. So this implies that these planetary precursors, as interpreted from the weather data, must imply they also experienced the similar the devolatilization process as the solar system rocky bodies. So therefore, the devolatilization is a universal observational phenomenon. So with that, actually, that's how tell you that we rely on stellar compensation, but it's not one-to-one to translate. And importantly, is that to consider this devolatilization process. And here is actually a review about how to use this phenomena to understand the planetary properties, including the ball composition, planetary multivariate interior structure, and the surface, and even atmospheric composition by just starting from the start. And of course, you also need to consider other measurements such as mass radius of the planet to be able to really quantify the detailed properties of the planet. So I will not go to the details here. Then just leave you with the procedure that this is something we can build a bridge between the stars and the planets. Okay, so this is mostly about for sun-like stars. So how can we use this actually or to understand the M-stars? Actually, before I talk about M-stars, are there any questions which stop you from following? Okay, I take it as a no. Okay, there we continue. So the reason we care about M-stars because M-stars are really abundant in our solar neighborhood, as shown here, and statistically, and every single star would potentially host at least one planet. So that also means this type of stars are also the class host the most of the planets. So therefore, we care about them. And also for the planets orbiting the M-dwarfs, so they are also the ones we will be most ready to measure because their shorter distance between the star and the larger effect they can cause onto the star, such as through like the Doppler effect or the transitive photometry. So that's why there's also a lot of like atmospheric characterization with the GWST also tuning towards the planets orbiting such stars. But from what I talked about earlier, by understanding the stellar compensation, and this is something give us a limitation. So the reason is because the M-stellar compensation is not as easy as the sun-like stars that we can measure. So then one of the practice that have been adopted in the exoplanet community is that we use the sun-like stellar catalog and to cut them and to make them to show to choose the potential K element, and then based on the measure the metallicity for the M stars, then we use the trend of the sun-like stars to constrain the compensation of other elements for M stars. But this technique has not really been tested, and this is something that mostly relevant to this work that we working on recently. So of course, just to bring everyone on the same page that why M-star abundance is challenging to measure. So first, because of the low photospheric temperature of stars, they can give rise to pervasive molecule bonds that can severely distort the spectral continuum. And as you see here, for example, with the titanium oxide, and this actually influence a lot about the atomic lines of other elements. And this problem will become even severe when you go to the cooler and cooler stars, as shown here from M1 to M7. And so, however, this issue actually can be reduced by going to the near-infrared regime, where the flux is enhanced for M stars, because of the energy distribution, and as shown here, like from the CARMENES spectral atlas in the Y band and H band, and this spectral become much clearer compared to optical spectral wavelength regime. And indeed, so here nowadays we have like a bunch of high resolution near infrared spectral measurements. So these slides I took from Haiyang, and she is also the referee for this work. And so here we collected the data mostly from the three surveys, from Apogee, CARMENES, and Subaru, the infrared Doppler instrument. The reason is that because these surveys give us the most relevant computation for the elements that of our interest, and also they are analyzed with the similar the atmospheric model, and I will talk about it in more detail. So yeah, so here is the collection from these three sets of the surveys from Apogee, and from so here shows the faintly marked sample of 24 M-dwarfs analyzed in the H band and with the model atmosphere marks. And here I show this NAM pair of the elements versus the metallicity, and this NAM pair of elements. By the way, this is the mostly interesting and important ones for understanding the rocky planetary properties. So yeah, so then we also have like the Subaru survey, and here it shows their proof of concept sample of 13 M-dwarfs and analyzed in the YG and H band, and also with the same model atmosphere. And again with the CARMENES, here additional 6 M-dwarfs, and also analyzed with the marks and also in the YG and H band. And as compared here, so they show this quite a similarity even across these different surveys, and this is also one of the reasons that we combine them together and to form our first set of the M-dwarf static computation. And also thanks to Alavika that she later pointed out that actually in our data set there's two stars overlapping with each other from the Apogee and CARMENES, and so these are two stars are showing the collectors. And when the analysis are available for both surveys, and you might see this like they are overlapping with each other even though with the relative larger uncertainty. So clarify that here is that there's 43 measurements, but for 41 stars. So then for the GK dwarfs, this is what we collected actually from the GALAH survey, and this is the Australian stellar survey, particularly for the galactic archaeology purpose. But they reached to like about 5 kpc of the solar neighborhood, and with relatively good resolution. And here I extracted the stars, particularly for GK dwarfs, from their catalog, and then here I show with this lofty and effective temperature diagram, and then further classify our GK dwarfs into the different populations, into the thin disk population or thick disk population, and also halo stars. And also for our interest, for this work, we focus on the thin disk stars because they are positioned mostly ones similar to our sun, and this is what we know and what we would have the more confidence to characterize, particularly for the planetary purpose. So here I showed just how we selected the thin disk stars based on the baseband 2014 criteria, and this is by calculating the ratio between thick disk and thin disk ratio, and you might find the details in the work. And then the right panel shows on the tumor diagram to show how this kinematic data would behavior for these different parts of the stars. But to emphasize, this classification only based on the basis of the baseband criteria instead of instead of this diagram on the right. So now we have had our M-dwarf data set as well as the GK-dwarf data set. Then we started to do the comparison in the preliminary phase. So first we did the Pearson R-linear correlation to test if there are indeed correlations between the XH over IPH. And indeed it shows here that for the most of the elements other than carbon oxygen, the correlation in coefficient larger than 0.8, it shows the very strong correlation. While even for carbon oxygen, also about 5 to 6, so that's also acceptable level. So this correlation, so that's also depends on the p-value. Then we are confident to actually to fit the trend and to understand this further. So in the rest of the talk, I will focus on these 4 elements: carbon, oxygen, magnesium, silicon, just for the clarity. So then, first, based on M-dwarf sample, that because, as I said, we have only 41 stars, 43 measurements, and the data set is relatively small. So to be able to get a good sense about what potential the population of M-dwarf, their composition would be, that we employed the bootstrapping technique. And using the bootstrapping technique is actually you sample your original data set to the equal size of the size of the original sample and replace them. And you allow the replacement. So that means you potentially can sample the same data set for twice or 30 times, but always keep the same sample size. And then you can generate the equal size of the sample. And then I generate the process for like 2,000 times. And then for each sample size, I did this like I did this like ODR fading and to get the trend. Then combine these 2,000 size of the ODR fading and to get the best parameters for the slope and also the intercept for the beta. So this would actually help you to overcome the limit in the sample size and achieve a reasonable uncertainty of the fate. So for the GK-dwarf data set, it's actually the problem is the opposite because the data set is huge, and our M-dwarf data set is relatively small. So you will encounter the problem, the imbalance of the sample size. So to make them to be more comparable, what we did here is that we resample the GK-dwarf data set and to the equivalent size as the M-dwarf data set, and then we apply the same ODR fading and to the resampled GK-dwarf subset, and also repeat this for the 2,000 times as well. And this actually would give you actually a more robust trend, particularly for the uncertainty of the regression. So then with this, the different techniques applied for these samples and to get a trend, then we would be able to ask are these trends statistically consistent or not? So this actually would actually can be translated to understand if the fitting parameters of the two sets of the trend would be consistent or not in terms of the hypothesis is that, for example, alpha and beta, if they would be identical in that sense, if the statistics of the parameter size larger than critical value, or the p-value is less than 0.5, in that the null hypothesis will be rejected. Otherwise, the null hypothesis will not be rejected. So this is the simple idea to test this with these two parameters. So the techniques that we apply to do this null hypothesis test is the Mahalanobis Distance test. So I'm not sure if everyone is familiar with this, but just to be clear with everyone that, so this technique actually, the only difference of that from the Euclidean scenario is that they take into account the covariance of your parameters, which is the case for this scenario, because the alpha and the beta here are correlated to each other. And so it's important to take into account the covariation. covariance to do such a test. Then we also have now like a two sample problem. So here we got the two samples and in the two dimensions, and then we can calculate actually the MD statistic based on the equation here, and of the S here represents the pooled covariance, which is the details of this technique, and then you can calculate the statistic of this test method. And with it very very good with the test method is because it follows a simple and intuitive chi-square distribution, and also with the p degree of the freedom, with p indicates the dimensions of the variables of this data set. So with that, actually, we can also take into account of the uncertainties on your data set. That's what we implemented for this work. And also there's open access code now available on GitHub if you want to explore this for other purposes. So by employing this technique, then we applied it to the alpha and beta data set for GALAH and M-dwarfs. So here is our test outcomes based on the calculated p-value as well as the statistics. So you might notice that for carbon, oxygen, and magnesium among the dwarfs, they would be rejected based on their value, where for silicon, you might see the p-value is about 0.04, so it's very closer to the rejection criteria. And to some degree, the rejection criteria is arbitrary, so 0.05 is chosen for the CARMENES in the statistical analysis. So then we label the silicon here as the question mark, and then we will try to follow up on this further. So then here shows the full panel of the test results for these 9 pairs of elements, and we also got for like a sodium here, which is a clear non-rejection case because the p-value is very high, and otherwise this null hypothesis can be rejected, especially for silicon. I will talk more about that. So upon this result, and one of the key concerns of this test is that the sample selection. Even though we have gone through as careful as possible to select the data set with the mostly relevant, but still you could also choose the different samples for your test purpose. So the upper panel I show what we adopted here is the full sample of a GALAH database, which is up to 2.4 kpc, and also select the samples from Apogee, Subaru, and CARMENES, which actually contain within about 150 pc of the solid neighborhood. And so here is the 3 particular elements with the question mark rejection and non-rejection and clear rejection case. So then we also think about depends on the distance of your sample. So we also tested the GALAH database with also within 150 pc of the solid neighborhood, and to see what is going on here of these two two subsets. So here is the test outcome. Again, for silicon, it will be like a marginal rejection case, and while for sodium and nickel, it's because
sorry, Haiyang, I cannot hear you. Can you hear him? Others?
No, also not.
No.
We lost the sound.
Yes, something happened. Haiyang, can you hear us?
Near infrared spectrum and the same pipeline and similar pipeline and same model atmosphere. So then here is the test outcome.
The single empty scenario, and we got the silicon become clear rejected, while for sodium it become like a question mark on the rejection, where for nickel it's non-rejection case. So you see this inconsistency between different sample selections. So indeed, this will play some role here. So to be able to reach a conclusion is that we actually combine all of these 3 different sets of tests, and for the silicon, we label it as the marginal rejection case by considering all the 3 different cases. And then for sodium and nickel, they would be either non-rejection or undetermined, because as you see in the red and blue, they show this conflict between for the test outcomes. So this is just the summary with the test p-value of the 3 different selection of sample. This will give you a relative intuitive sense which elements are statistically inconsistent between the M-dwarf and GALAH, which ones are actually questionable or even that need to be further examined. And then, okay, then the question is, what can we learn out of this statistical test? So one particular thing I shown here is the magnetosilicate to carbon dioxide ratio, as I showed earlier. I hope you agree that this is very important for understanding the planet property to first order. So actually, based on the GALAH, which is in the background of green dots, and M-dwarf, the brown dots on the other front, you will see that for these 2 K elemental ratios, they show this difference in terms of their trends. So actually, this highlights how in that if we constrain our M-dwarf static composition from the sunlight static composition, that it may distort our interpretation of the planetary properties for those around the M-dwarfs. Okay, so later we try to imply to understand what's going on here. For example, how the metallicity plays a role here, or in terms of age or galactic chemical evolution. Indeed, you see here color bar by the metallicity. Clear to see here is that with the higher metallicity, the magnetosilicate ratio also decreased, which also makes sense from the chemical evolution perspective. So this indeed shows that some these physical reasons play the role here in determining these differences. So then we also made additional like bonus test to see if we test on the XFH versus metallicity space instead of XH over metallicity. What would happen to this test outcome? So here is the result, which shows that actually, except the silicon and the titanium, and all the test results would still hold to the one that we tested on the XH over metallicity space. Of course, for the titanium, the regressions are not reliable, as you see here. So this is to give you a sense of how this galactic chemical evolution influences test outcomes, and which doesn't change significant to our results. So another thing is considered is about the atomic diffusion, because for M-star and GALAH, we have a different level of the atomic diffusion. So here it shows animation for the GALAH with the high precision analysis. You might see here is that if the focus on GALAH, the effect, the diffusion, atomic diffusion cost is about within the range of 0.5 to plus minus regime. And this is indeed is also what one of the data sets that we collected from the Apogee survey, and they also concluded for the mean abundance differences between the M and the GK component in the binary systems. Then the mean value would also be about 0.5 plus minus 0.3. However, you may see there's a large variation of the differences with up to about 0.2 axis. So this may imply that atomic diffusion may not explain everything here. So of course, it requires more measurements and comparisons for the binary MGK components if you want to understand better about what's going on here to cause the differences. Okay, regardless, so the chemical trends XH over metallicity between M and GK dwarfs are not necessarily consistent with each other. Of course, upon the selected available chemical abundances of these dwarfs and also adopted statistical methods. So this actually carry crucial implications for two thoughts. So if the observed differences are physical, such as due to the intrinsic difference in stellar formation, evolution, including atomic diffusion, that this imply that the inferences of M-stellar abundances based on solar-like abundances will place incorrect constraints such as carbon toxicity, magnetic iron-to-magnetic ratios, and shown to you that on characteristic exoplanets. And this could be relevant not only for rocky planets, but also even for gas giants for the planet around the M-dwarfs. So on the other hand, if the observed differences are unphysical, such as due to the inaccurate M-stellar model M spheres, the line list choices, and the fundamental parameter estimations. So probably if that's true, then we need to pause for 1 second on applying the current abundance modeling techniques, which is potentially calibrated for the sun-like stars and to the overall set of M-dwarfs in the larger surveys, such as now going on for the Apogee, Subaru, CARMENES, as well as for PLATO and ELT, which are in the near future. So to conclude that an investigation of dedicated modeling techniques for M-dwarf photospheres, as well as increasing size of benchmark homogeneous abundance analysis are recommended. So with that, I would acknowledge the collaborators with me, not only for this particular work, but also for the exoplanetology part. And this diagram summarizes what the test outcomes for M and GK dwarfs. And I would really thank you for your time and attention. And happy to take any questions.
Okay, Haiyang, thank you very much for a very nice and interesting talk. And we have now time for questions. So please, okay, Paul Christofari, so please. Yeah.
Yes, thank you. Thank you for this very interesting talk. Very straightforward, simple question. I'm assuming in the sample there's some M-dwarfs that are magnetic. Is this something you counted for, or is this, or do you have a sample of very inactive M-dwarfs because they were targeted for planet search?
That's a very, very good question. Yeah, no, here we actually didn't really consider the stellar activity planar role here. And as you mentioned, because most of this data comes from for the purpose of characterizing planets. And unfortunately, I also don't have the data for the age of these M-dwarfs. So, but I'm ranking that they mostly would be very old. So then for this data set, potentially maybe the stellar activity for this M-dwarf sample maybe already not that active anymore. But this doesn't imply that the early stage of stellar activity will not influence the stellar composition. So, indeed, okay. Does that answer your question?
Okay, so somebody else? We have still enough time for many questions. So to keep some time for you, may I ask you, can you please go for the slide with your conclusions? And you, just the previous one, yeah. You mentioned here two possibilities. One, that it's physical. Another one, that thanks to Wang stellar atmosphere models or parameters like line list or oscillator strengths and so on. So what do you think, what from these two possibilities is more likely? That it's really there is a difference, or just that we need to improve our modeling?
Yeah, actually this is gonna be question very hard, challenging for me to answer. So actually that exactly outside this is more from the exoplanet point of view, and to try to use the M-dwarf data and that calibrated from stellar composition to see how the sunlight stellar composition to see how that influences. But we came up with that this potentially have both role playing here. We are still not that super clear actually which would be most relevant here. And as I mentioned here, this M-dwarf data, they actually use the Max model, and they are potentially calibrated for sunlight stars. And of course, here we also have even use the same model M-scale like Max, and you have different line list and across different pipelines and across different surveys. So this indeed we was exploring to see the cross catalog calibration and to see how this would potentially play impact on these differences. And also, as I mentioned earlier, that regarding like atomic diffusion and also potentially the galactic chemical evolution, this also demonstrated towards the way that it may, from my current simplistic point of view, it may play some role here to influence the differences. And also, there's another thing that I have not really investigated, which is the actually how the effective temperature of this stars, because the effective temperature across this stars span quite a wide range. How this actually the effective temperature are correlated with their stellar bonuses, which is not or still some like remains in there. So so this also an additional question actually to check. So to be clear.
Mm-hmm. Okay, thanks. So somebody else would like to ask something? Okay, Carlos.
Just along the lines of what you just mentioned, Haiyang, now that there could be variations with temperature. I think you know, when one worries about systematics, that in the case of M-dwarfs will be associated to the presence of molecules and convection, then mainly, right? Then I think it will be quite interesting to search if there is a correlation of the trends with temperature, because things will get really much worse in that regard within the realm of the M-dwarfs with temperature as you reduce the temperature, right? So whether there is a trend or not, it will be crucial, I think, in signaling systematics.
Yeah, indeed. Actually, I completely agree. Actually, for the M-dwarf data that we collected here, and the like in apogee, they calibrate the difference between the abundances with versus the effective temperature, and they do not see like significant difference here. But for the GK dwarf, which is quite interesting. Actually, I might show this diagram. What being here? Yeah, you might see here, right? So here is from the GALAH database. You see, actually, they do show this somehow the trend here, particularly for carbon oxidation, even though not for most of the other elements. So this, we have not been very sure if it's because of the carbon oxidation, because it's harder to measure accurately. So toward the lower temperature, they have fewer data available to so cause this trend, or it's really something still like correlation with their abundance versus the effective temperature. And I also test on the apogee, and they also show somehow the trend, but are not consistent across the elements. So as I said, this is still something like worth exploring, even for the GK dwarf side.
So there is not another question.
Well, I somehow I don't find the button for the hand.
Okay, so please go ahead.
Yes. Okay. Thank you very much for your talk.
Yeah. Hello. Yeah.
Yeah, also a question related to the last topic. So you said you're right that we should pause applying the techniques to large sets of M-dwarfs, but if you want to study trends for example, with temperature and so on. Is that possible with the current available abundances, or and using similar statistical methods for the sample, or wouldn't we need more abundances, even if if the models are not perfect yet just exactly to study the models?
So I would say like first start with the binary systems. If we can have like more measurements for the M-dwarf compensation directly in the binary system, and now we have only like really few available here. So this would be something more relevant to actually to understand this impact from the effective temperature, and also calibrate the influence out. And of course, we need more measurements for M-dwarf data. So this is a little bit counterintuitive. I said, okay, we need a pause for 1 second, but still we need more data to be able to clear. So in that sense, also this may imply that can we actually build some like a better pipeline or more tuned towards M-dwarfs, and which actually can give you relatively more accurate representative of M-dwarf data, such I know some aware of some like scattered surveys are doing that work. Then potentially we can reach more confidence in terms of these test outcomes. Yeah, with more data available. I hope they're also more accurate.
Another questions? Somebody else would like to ask something? So in chat, yeah, there is also nobody. So if not, so thanks, Haiyang, again. It was really very nice talk and nice discussion. So thank you very much, and yeah, have a nice day.
Thanks a lot, everyone.